So this session is going to discuss the estimating the value or the T&D marginal cost. Really, it's an avoided cost value that simply is doing a comparison between here's the costs on a per kVA or incremental load growth value versus with and without the need for the infrastructure upgrade. Now, there's a couple inputs that really influence the value component. So before kind of diving into the results, I want to walk you through and highlight here's the things that really are going to influence the results. Obviously, the ratings and the risk tolerance are going to determine how likely are you to trigger an infrastructure upgrade, and will have an impact on the value. Whether or not you apply a probabilistic 1 in 2 or 1 in 10 weather year will influence the likelihood that you exceed the ratings, which will in turn trigger the value scenarios, because if you are not expected to exceed the design ratings or the long-term emergency ratings, you are very unlikely to have any value at that location. We also have some boundaries here. We have a boundary in terms of the deferral period, where you can kind of essentially instruct the model to restrain deferral. Say the most we can defer a project is 10 years. After that time span, we need to do something about it, and it can be deferred indefinitely. And then we have another toggle here that says, well, if we're really looking at deferral of a project, we may want to consider the magnitude of the resources needed, whether it's for demand reductions or power injection at the site or batteries, because I may want to cap it, and say, look, anything above 20% of the load is too much and cannot be delivered through the ERs because there's an actual cap on the potential at that location. That's adjustable. And then we have other components that look at infrastructure upgrade costs and all the financials. So the infrastructure upgrade costs are a key determinant of the value. Pretty obviously, the higher the number, the bigger it will be. Asset book life just determines how it's spread over time, and obviously all these other inputs that are financial. So that being said, I'm going to hit the estimate value button, let it run, and quite simply, what it's doing is taking each of the scenarios that were implemented and calculating, would you have needed an upgrade? Yes or no? If so, what year would you have triggered an upgrade? Given the uncertainty in growth patterns, how long would you have been able to defer that upgrade? And here's the financial implications. Here's the megawatts needed to defer that upgrade, and here's the financial implications. So it kind of runs through all of those scenarios one step at a time. That's a number of calculations. It's doing this with all those simulated load growth trajectories, and in this case, 5,000 different simulated load growth trajectories, and looking at the design criteria that was input and the tolerance that was included here. So a lot of times when you look at the summaries, you show both the case of the point estimate as well as the distribution of the results, because you can have circumstances where you have zero value in 40% of the simulations, but have relatively high value on 60% of them. So it kind of shows you that full spread. So with that being said, the data crunching is all finished, and the results for the estimate value are shown in the value tab. And here we'll walk down through the interpretation of these one by one. So the first one is looking at the avoided cost by forecast year, and it's a dollars per kVA basis, and that's simply saying here's the savings on over the thousands of scenarios and per kVA that we expect if you're able to defer this project. And it's low in the initial years because the chances of deferral are relatively low for the initial years. It climbs up over time in this case because there's a higher likelihood of a need for deferral later on. And then it dips down again because under most scenarios, by this point, you have already implemented the deferral you're done with it because you had to implement the upgrade. So you have no additional value. You have essentially a new area substation or whatever's needed, for RDRJ. So that's the first chart, and it's really a summary of the expected values. Now these same results can be seen in table format, and what you see here is these bar charts are going to align exactly with the expected value. But what the table is showing you is the underlying variation in the results. It shows you that, look, there's scenarios here, the bulk of a large number of them that have no value, right? So that's over 25% of them. And here it kind of gives you the actual exact number of scenarios without value, either because the deferral wasn't needed or you couldn't defer it because the growth was too fast. And then we basically have the range of results. And the expected value is obviously an average of every single iteration and run, but there's ranges of results that go from, well, it would have been you had low savings and need a lot of megawatts to defer it, so you just need a little bit of resources to defer it, and that could defer this investment, which is quite substantial. So that's the distribution, and it's annual basis. In the bottom, we show what is basically a 10-year levelized cost for that location, which essentially is taking years 1 through 10 and taking the levelized value for that time frame. The third chart here is the year by when the deferral is needed. And again, you don't necessarily know what the growth will be from year to year, and you don't necessarily know what the weather will be from year to year. So when you factor the uncertainty into the analysis, you can end up in situations where you can say, well, there's a X% chance that I need it by 2017 or 3 years out, and there's a X% chance that I need it 4 years out. So what this chart is kind of showing is saying, well, here's the likelihood or the percent of the runs where you would have triggered the need for upgrade in each of the various years. So most likely you want to beat the hump if you're actually trying to decide when you want to include when you want to do a deferral project, if you're really looking at it seriously, because oftentimes if you're past the hump, it might be a little bit too late, or you need to act very quickly. And the last component here is we have a component that indicates here's the situations where no upgrade was needed over the analysis horizon. Now in this case, it's a fabricated example, so we pretty much need an upgrade, and the likelihood that you don't need any upgrades is relatively low. The next chart is looking at how many years can you defer a project. And again, this kind of rolls back to the uncertainty in the load growth and the variability from weather from year to year. You can, in practice, go into the project and say, well, we think we can defer this project for 5 years, but load growth may be faster than you anticipated and what your analysis of the historical load data told you. So therefore, you had a shorter deferral period. Or it can be the reverse and actually go slower, or the load can start declining, in which case you can have a much longer deferral period. Or you may just get lucky and essentially have a series of not extreme weather years. So you did not get the really extreme weather year over that 8 or 10 year horizon, and therefore you did not have a situation where you were repeatedly exceeding the design ratings to the point that you exceeded the allowable risk. It's a useful chart. One key thing to keep in mind is that really it's the same investment you're deferring. And say it's a $50 million upgrade or a $10 million upgrade, I think is what we put in the input overall. If it's a $10 million upgrade, then you're basically, if you defer for 1 year, it has a specific value. If you defer for 2 years, it has a specific value. And that's what the chart down here shows you. This is the total value, in this case in millions, if you manage to defer the project by 1 year versus if you manage to defer it by 10 years with all the increments in between. So a 5-year deferral is essentially worth 4.66 million, whereas a 2-year deferral is worth 2.5 million. So this is a key element in terms of the financial aspect of trying to identify when you want to shift and look at not just simply a traditional upgrade, but look at a non-wireless alternative, because you have to factor in the risk of being able to have multiple years of deferral, and also the value of having multiple years deferral versus a much shorter deferral. Chart number 6 is kind of saying here's the megawatts required for each of the deferrals. And it's capped, based on our inputs at 20% of the load, and it's capped at being most 10 years. So one of those kind of came out and say, here's what the number looks like. And the reason it varies, this one really assumes that you actually can ramp up the resources in tandem with the need. So it does not, it assumes relatively great foresight. In practice, you actually will pick a value and say, we want to have a schedule that gets 2 MVA by year 1, 3 MVA by year 2, 5 MVA by year 4, and potentially stick with that. So there's a bit more risk when you fix the number as opposed to have perfect foresight. But it's a useful set of information, at least in assessing the amount of resources that you think are needed. And we actually give you the summary statistics here as well. The latter charts are showing what is essentially the total value per kVA. And to be clear, this is the revenue requirements under scenario where you do have to build as you normally would versus a scenario where you deferred building to a later period. And it has the its total value, so it's not annualized. So for example, if I had a revenue requirement that is, say 16 million, and I deferred it for by 5 years, I'm going to have a different NPV based on the value, and take a look at the difference between those, the with and without deferral scenarios, and calculate the values and look at the KVA associated with it. So what this is showing is the variability, by number of years of deferral, and it shows you here's the bands. This chart is known as a box plot, and it shows total value in the y-axis. It shows the number of years of deferral in the x-axis, and the box itself has a line in the middle. The middle is basically your median, or your most not your most likely outcome, but the middle value. So that line right in the middle of the line is key overall. The box itself represents 50% of the outcomes. So that's basically saying the best chances that you're going to be in the box somewhere in there. And then those upper extremes are basically showing you the extreme edges of the results. It excludes the really, really extreme outliers, but it just kind of shows you here's the potential range of outcomes that we can anticipate. If we have a deferral of 1 year versus a deferral of 10 years. Now, because this is looking at total value, and we haven't taken, say, to make this concrete, an example where we have 4.7 million in savings. We are counting the total value divided by the MVA needed. We haven't annualized it. In practice, we can take this value right here, and because we're going to have 5 years of deferral, annualize it or spread it over the 5 years where you would be having the deferral. So it's essentially financial calculation that spreads that revenue collection over those 5 years. And in doing so, you get this chart. So it's similar to the one above, except that in this case, we're annualizing the values or spreading them across the deferral years. And the concept is the same. It gives you a sense of, if I had a deferral of 1 year, here's the range of potential outcomes and value in dollars per kVA. And if I had 5-year deferral, here's the range of values, etc. So it's pretty useful. And below it, we have charts that show the outcomes for each of these. So to recap, the bottom ones are more complicated, but at a very high level, we have a few quick summaries. We have a summary of here's the value of deferral per KVA, which is a key element in terms of decision making. And then we have information about when deferral will be needed and what the risk is, what the length of deferral could be, and what the probability is of different lengths of deferral based on what we know. And here's the value tied to different amounts of deferral. This one doesn't actually have uncertainty. If you defer something for 4 years, you're going to get that value. Or 5 years, you're going to get that value. It's a question of what's the amount of MVA you need for that, and whether or not you're going to get 5 years or 2 years of deferral. And then we essentially have the backlogs required for deferral. So in sum, this is providing you some key information in terms to allow you to compare between going for a wires option versus a non-wires option. The non-wires options do have to be cheaper, in order to provide some value. And there's a component here where you want to likely incorporate risk in the decision-making process as well. So with that, that wraps up the value portion, and we're going to talk about producing a report.